Welcome back. This is lecture 11 in our series, and today we're going back to the questions of cross-sections and how to obtain those cross-sections from the objects we already have been looking into in our formal development of the theory, which are the endpoint correlators, endpoint functions, endpoint green functions, call it however you prefer. So what we did in the last lecture was to define a bunch of quantities, right? So the first things we defined were the cross-section and the decay width, right? This is a particular case where you had essentially what you could call a scattering from 1 to n particles. We call that a decay, or more generally, there's the scattering of m particles into n particles, which we call the cross-section. And I try to argue that these are proportionality constants between the geometry and the number of events that actually happen. So they encode, given a particular geometry, how probable is to generate events. And that's an intrinsic property of each theory. Some theories are stronger, they interact, cause more interactions. Other theories are weaker and more weakly coupled, and so produce less interactions or scatterings given the same geometry, right? So that's the information that cross-section and decay width encode. And then in order to make some contact with the endpoint functions that we have been developing, I defined the S matrix. So the S matrix is this evolution operator here that makes the contact between an asymptotic state in the infinite past and a asymptotic state in the infinite future, right? So the job of the S matrix in the limit where this guy is defined at a time infinitely distant from this one is to do this the whole transition. So evolve this guy from the past into a intermediary point, and then evolve the resulting, and then of course once you evolve these asymptotic states to any arbitrary time, intermediate time, they interact, you generate the outgoing states and you evolve them until they are asymptotically free again. And that's what the S matrix does, right? So it's defined in this equation. And then I also define the T matrix, which is the part of the S matrix which is just not, it's just the part that is not the identity. So it's the part that I don't want to, I'm not really interested in the cases where the particles just go through each other without interacting. So I define T, and finally I define this invariant matrix element, which is just the part of T that encodes the dynamics, right? Because this part is just kinematics, it's just conservation of momentum and energy, right? So really the information about the dynamics of my theory comes from this part, which is also Lorentz invariant, which is very convenient. And then I didn't prove, but I told you that there is the LSZ reduction formula that actually connects these elements of the S matrix, right, with the endpoint functions, right? So essentially what you do is that you look, right, that's another thing that I just said but I didn't prove yet, that if you take an endpoint green function, so say you're doing a scattering 2 to 2 particles, right? So it's a total of 4 momenta involved, and you take the 4-point correlator that will depend on these 4 momenta, and you put each of these momenta on shell. That means I take p squared to m squared. Then I told you that this green function will have propagators. That means that point where every momenta is on shell is very singular, because you have a propagator that has a singularity exactly on that point, right? So the 4 propagators will be on their most singular point. That is the residue of that pole is the S matrix element. So that gave us a way of going from the green functions, right, to the S matrix. What I didn't tell you yet, and that's what I indicated with this missing here, is the connection between the S matrix and the cross section, because then we know how to compare this with experiment. And that's what we are doing today. So we want to now complete this connection. Let me start with the probability that if I start with a state that is just phi A, phi B, right? What is the probability of producing, let's call this P, right? A final state that contains n particles, and these n particles are in the momentum interval dp1 to d3pn. So I'm putting each particle as very narrow momenta for now. I can always integrate in momenta later to get more possibilities, right? So I'll call this P AB, which are the initial particles, going to 1 to n particles. And this is not the total cross-section or the total probability of event. I'm really demanding that this is in this interval. So I have to have a product here of all these D3PF, and this is the normalization, right? 2P cube to energy final, and this is, I have one element like this is just the relativistic normalization, and I have one element like this for each final state, right? And in here, of course, I'm putting P1, P2, Pn out, and phi A, phi B in square, right? I'm taking the amplitude that I had from the S matrix and I'm taking the square of it. Of course, if I integrate over all the final momenta with some wave functions, then these become a phi 1 to n, right? But I'm taking just in a very narrow interval of momenta, so I left with this element in front. And this encodes the probability that given that I have a state A coming here and B coming from the other side, what's the probability of scattering in this specific momenta? So I'm taking very narrow windows. Now imagine I do a little bit more realistic version of this. So now I have a beam. Let's draw a circular beam, right? And this has many B states coming, right? They are all very similar between themselves, right? And now I want to know what's the probability of producing a certain number of events once that beam is going through, right? So the number of events will be given now by the probability. This is the probability of one of these guys scattering, right? So now I have to sum over all the incoming particles, right? All the particles B coming over here, because any of them can produce an event here, right? And of course, this is if I want to do a sum over all of them, but since usually the number is great, it's much more useful to define a density, right? And write this so I can put some kind of reference frame right in the center of the beam here. And there's a vector B that gives me a position in this cross section, now this section of the beam, right? So I can integrate over this area, which will be an integral of d2 over t to b, right? And define a number density, which is the surface density. If I cut the beam anywhere, that's the density of states here. And then there's a probability that depends on where the particle is. In fact, the way I define B is the distance from where A is going, right? I already defined this B before. This is the impact parameter, right? So I'm defining the distance from the line where A goes, and B runs in the plane perpendicular to the direction that A is coming, right? If the beam is uniform enough that this density does not depend on the position, I can bring it outside and write NB D2B P of B. And then the cross section, right? As I defined before, the cross section, and this sigma is because I'm not taking the total cross section, right? So I'm taking narrow window of momenta, so that is not the total cross section. This is just a small part of the cross section. I have to integrate all over. Will be this number of events divided by the area, right? That's the definition I got to last lecture when I had a beam inciting into one state. So I'm using A as a target, and a beam of B is hitting at A, right? I can always do the same for A, create a volume, and then the cross section will be this same number divided by the number of targets, the number of A. Remember, I can put NA here and use many A's, but for now that's sufficient for us, right? And of course, if I divide by the density, the conclusion I'm getting is that this is just the integral over B of the probability that depends on the position. Of course, there is some dependence, right? The particle B passes too far away from A, you expect it won't interact, and that's why I'm assuming this probability will depend on the distance, I mean this impact parameter between A and B, right? And that will show up later. Now I just have to substitute this expression down here, and what I'll have is that the cross section, the differential cross section, right, is the integral over B of that many small interval in momenta of the final particles. So this is sum over all final particles, 2 pi cubed, to energy final of any of those particles, times out, and this is the square of the set of all final momenta, phi A, phi B in square. Now I have to be very careful about this, right? And remember that this guy is just, of course, PF phi A, phi B times the complex conjugate of this, right? PF phi A, phi B star, right? And I'll write phi A, this state phi A, phi B, in the way I defined before, right? If you remember, that guy was defined as phi A, phi B equal to the integral in momenta d3ka over 2 pi cube integral d3kb over 2 pi cubed times the wave functions phi a that depends on ka, a wave function for phi b kb, again normalization since we want to keep the relativistic normalization to EB, and I left some part of the phase of this guy explicitly here to carry the dependence on the impact parameter. So this B is the same as that one, KB, and of course the momentum eigenstates KA, KB, incoming. Right? And I'll have to do this for this phi A, phi B, and again for the complex conjugate. But again, but you have to be careful because there's two integrals here, and I have to put two other integral variables for this part as to not have. I mean, there are four integrals in momenta when I do this, right? Because Ka is just a mute variable, and I have to use four of them. So I'm doing that over here. Here, and let's see. So this part just repeats itself. Then I need to write this one. I'll write these two integrals as just one. So I'll put a product over I going A or B. And I just have to write the integral of d3ki. That way I have ki and kb over 2 pi cube. Let me just increase this a little bit. So this is, let me do it like this. It'll be more clear. So the product is over everything that's inside. Not always easy to deal with this program. Phi I ki, right, which takes care of these two terms. Square root of 2 EI. And I have another one for this part, right? I'll call I have the same expression, right? I'm still missing the exponential. I put that in the end and this part, but it's the same expression again. But now I'll just call d3ki bar. So this bar indicates the ki, ka, and kb for this complex conjugate part. I have the 2 pi cube again. I have phi I star because now I'm taking a complex conjugate of ki bar vector divided by 2 EI bar. And the bar here means I'm taking ki bar as the momenta to calculate this energy. Right? Then I have two exponentials, one with kb and another with k bar b. So this ends the product, right? There's this exponential of minus ib kb bar minus kb. So the kb part is just the same as this with the minus sign, and the other one is the complex conjugate, so it changes the sign, right, since it's coming from here. And this is multiplied by, of course, these brackets here. So I have PF, the set of Ki, out, in, and I have the complex conjugate, which is just PF Ki bar star, right? Out, in, which is a big expression, right? So you have 4 integrals here: Ki over Ki, Ka, Kb, and Ka bar and Kb bar. These are the 4 integrals I have to solve in order to make this integral into a more convenient expression, right? The first thing I can do here is to do the integral over the impact parameter, right? Because b only really appears in this exponential here. So these 2 integrals are easier to do, and mainly remember that b is transverse to the direction a and b are flying, right? So by definition, I'm taking this line of impact, and b is perpendicular to it. That means that I can write the integral over d2b of the exponential of I b, this one, right? Kb bar minus Kb to b, right? I can exchange b by, right, b transverse, perpendicular here, right? And of course then this product will be just a Dirac delta, but in 2 dimensions, forcing the transverse part of Kb to be the same as the transverse part of Kb bar. Right? This is just a Dirac delta in that transverse plane. And now I also want to use in here, now that I have just momenta here, I want to use the definition of my invariant matrix element, because remember, we have defined event, right? What I'm calling here cross section is something proportional to the number of events, and what I call that event is when there is a scattering. The case where they just go through is not called an event, right? So that means that in this part I only have the part of the S matrix that actually scatters states, which is the T matrix, right? So in here I only want to include in this S matrix elements the ones that come from the T matrix. So and remember the definition I use for the T matrix, so I can essentially rewrite this guy as I invariant matrix element of Ka, Kb going to all the final momenta times 2 pi to the 4th delta Dirac delta of Ki minus the sum of all the final and initial momenta, right? So this is the total conservation of energy and momenta, right? Which will be very useful to help me with all those integrals. Right? I have a lot of deltas there, and of course in here this is just IT. So of all the elements of the S matrix, I'm only taking this part. And that's the only part that should enter in the cross-section, because by definition cross-section means scattering and not just going through. Right? So this part I don't want. Now, I can write a similar thing for the complex conjugate of this guy, but the complex conjugate that is showing here is in terms of k bar, so this will be just a very similar expression, but I have a minus here because of that I. This is the complex conjugate of m, and these guys are all real. I just have to be careful about the momenta, because this is defined in terms of k bar and not. Right? So I can now substitute these two expressions up there. So now I'll go a little bit faster, because I mean there's a lot of Dirac deltas to integrate here. So really I'll just kill a lot of these integrals in k, right, or in p, by using Dirac deltas. So I just have to really keep track of all the relations that will be imposed by these many Dirac deltas, and then I can just remove the integrals and force these relations in the end, because that's what the Dirac deltas do, right? They force some of these numbers to be equal to each other. So I have at least here 2 Dirac deltas coming from this one, right? I already integrating to b, so there's 2 here. There's another 4 here, and there's another 4 here. So in total I have 10 Dirac deltas to use to integrate these. Here I have 12 integrals. So let's see what kind of relation I get. I'll go a little quick with that. I won't do the calculations in detail, but I stress that you should do it carefully and check my calculations. Let's then take a look at these deltas. I have all of them here, color coded to make it easy to follow. And I'm interested first on integrating on KB bar. So I took these 2 deltas that involve K bar, right? The one that came from the integration in the impact parameter, and this one, right? That came from this invariant matrix element. So the first thing I separate the integral in d3k in the perpendicular part, which is 2-dimensional. Right, there's say x and y directions here, and I'm taking z to be the longitudinal direction along the beam. Right, this part, the perpendicular one, is easy. For b is easy to solve because there's this delta, so this delta goes away, and I do the integral in d kb perpendicular. Right, that implies on the blue delta Dirac here that I can, of course, separate into also perpendicular part, longitudinal, the z direction, and energy, because this was a 4 momentum. And when I do this integral, I can remove the bar from KB perpendicular. So this is just now an expression without the bars. I know that later when I use this integral, which is the delta Dirac, the Dirac delta that I'm not using here, right, I will impose this condition, and so I can also substitute KB perpendicular here by minus PF by minus KA perpendicular. I will use that down here. Right? So on this step, I only really did the integral in KB perpendicular. So I still have the KA perpendicular and the 2 longitudinal integrals. Right? This one is easy because of this delta. So that's what I do next. Right? So I substitute. I'm keeping track here because now all perpendicular k's are equal to their k bars. So in the perpendicular part, I already proved that k is equal to k bar. And I have to remember that inside these expressions for the energy, right, that involve all the k, all those k's. Right? Now I want to do the KBZ bar. Right? For that I use this delta, so this condition will be imposed everywhere else, especially here. That's what I did next. And now I have this integral in the DKAZ bar. Right? This is here. It's hidden inside here, right? I have the perpendicular and the longitudinal directions here. But it's also hidden here because of this relation, right? There's a KAZ bar in here. In order to see what that gives me, right? It's important to, I'll have to use this expression for the delta, right? Because I'm doing the integral in KAZ bar, and this is expressed in terms of energy, but I know the derivatives of energy in relation to KAZ bar is this. In relation to KZB bar is this one, right? But I also know that this is valid, so there's just a minus sign when I do the derivative of AB in terms of in relation to KBZ bar or KAZ bar. Right? That's just a minus sign. Right? And there's nothing else but the delta, right? So in the end, when I remove this expression from the delta, the rest is just the integral that will give me 1. So in the end, I just have to replace this integral by this expression here, in which I substitute the two derivatives in here, right? And this is 2 minus 1. And of course, this KAZ bar over EA bar is just the velocity of the A particle in the reference frame I'm doing this calculation, and VB is the velocity of particle B. And so what appears here is this relative velocity. Remembering that I have to keep this relation true, right? And so this is the answer of that integral. So I basically manage here to integrate over all the KA bars and all the KB bars, and the result is just that, right? But remember that those integrals were inside a much bigger integral, so I have to impose all the conditions that came from the deltas in the rest of the expression, right? And these are the conditions. This one fixes KAZ, right? Is what I used last to do this integral. The second one is actually two conditions on the two perpendicular directions for K, and this is for the longitudinal direction of B. Right? Looks like the conditions for KBZ and KAZ are a bit complicated, but I can show that they can be simplified. I already got rid of all those integrals. I also did the one in the impact parameter. Right? And I have this one left. Remember, I started with 3 of them. These 3. These 2 I used fully. This one is still there. In fact, I'm not integrating it in that condition yet, but I know that whatever multiplies this delta will have to satisfy the condition inside. Even if I don't integrate, I can already impose that on the rest of the expression, because eventually I'll have to integrate in that, right? And that condition can be used, so I'm using these 3, I'm calling this one 4 and this one 5, and by combining those, I can simplify the condition for KBZ and KAZ, which is done here. So if I put together 3 and 4, right, I just isolate this PF that is the same here as the final momenta in the Z direction, right? Here and here, and write this one. This implies that KBZ is equal to this, right? And if I put together 1 and 5, 1 is just energy conservation, 5 is the same, so EF, which is the energy of the final states, is the same. And that leads me to this expression, right? Which can be written explicitly here with all the momenta square and the mass, right? And once I know that the perpendicular directions, that's condition 2, right? Condition 2 tells me that the perpendicular components of the momenta are the same with bar and without bar. I can remove the bars here and here. And that means there's this number that I call a square here, just for simplification, right? Just to make it simple. It's the same that the one that is appearing here, and here is the same that is appearing here. And I have to replace kbz square by this expression. And that takes me to this equation, right? Which obviously has a solution for kaz equal kaz bar, right? If I remove the bar from kaz, this square root becomes the same as this one. And this one becomes the same as this one because these two pieces in blue here cancel each other. Right? So this is a solution to this equation. It is the only solution, but that's harder to see. Right? The way to solve the solution is to isolate square roots one by one and square the expressions again and again until you get rid of all the square roots and can solve for kaz square. That's a lot of algebra, so let's use a shortcut here. Mathematica can help us with that. So that's the same equation, right? I just call kza, kzb. This is kza bar, right? I put bar kza there, bar kzb, and a and b are those numbers that I had, right? And this is the substitution for bar kzb bar into that, right? So if I ask him to solve this equation, right, this is the equation we were trying to solve, and these are two solutions that he found. One is for kza equal kza bar, right, which is the one we found, and there's another one very complicated here, right? But we can test those solutions. Here I'm testing the first one. True means Mathematica can test that the left-hand side is the same as the right-hand side, which is obvious, right? And this is the test for solution 2, which is a mess, right? It could still be equal, and just Mathematica is not capable of simplifying it well enough. But for us, it's easy to see. This should be valid for any numbers that I put there for A, B, and the momenta, right? So I just put some random numbers there, and you see that at least for these numbers, this equation is false. That means at most will be a particular solution for a very specific case, which does not interest us. So the solution is really kza is equal to kza bar, right? So this is the solution that I found before. If I go back to condition 6 with that, and kaz bar are the same, that means kbz bar and kbz's are the same, and then both the perpendicular and the longitudinal components of the momentum are the same, that means the energy is the same, right? So I basically prove that all bar variables are the same as the ones without bar once I start doing the integral. And so that means this is the expression I have for the cross-section, fully written here. This is just copied from above, right? And then I will impose this condition. So all bar are equal to the ones without bar. I did these integrals, and I did this one, right? So then the result is I can copy this down here. These ones come here, right? But now, since I can remove the bar, phi star becomes the modulus of phi square. The square root of energy comes together with this one that I can remove the bar now. This is 2ai, right? This is what came from the integrals. Remember, when I was doing the integral, the only numeric factor that really appeared was this, right? So it is there. It is there. These two guys, m and m star, also now can become just the modulus square of m, because I can remove the bars here. And I'm left with this energy momentum conservation that I said I didn't use yet. Right? I could use it to integrate on this, but I won't. I will use something else to integrate on these integrals, because I want to keep these as long as possible. This is very physical. Right? It's just the total energy and momentum conservation, and I want that explicit in my cross section for as long as I can, right? And that's why I'm not using it yet, although I have imposed that it is valid in order to get here. Let's now bring this a little bit closer to what happens in a laboratory, right? And remember that usually when you're doing these scatterings, right, you don't know the position of the particle in each point of time, right? So position is usually not very well known, but you know fairly well the momenta, right? You know the energy of the beam. You know when your particles come out, you basically, your detector determines how much energy and momenta they carry, right? So momenta is fairly well determined, but within experimental limit, right? There's always some uncertainty in momenta that we have to take into consideration here, because we don't want plane waves. We want these particles to be at some point they are far enough from each other that they are not interacting. And again, that's what happens in the laboratory, right? They're basically free, they interact and they go away. The way to put that information here is to say something about these wave functions, which we assume nothing so far, right? What we want to say about them is that they are narrow enough to be narrower in momenta, right? They are narrow enough in momenta that they are narrower than the resolution of our detectors. That means that for the detectors, they will appear to have well set momenta, right? But which is wide enough to make these guys not into plane waves. So I just want narrow distributions in momenta, right? The easiest way to do this here is to assume they are Dirac deltas, right? But this is not critical, right? This is just the easiest way of doing it. I could just assume that they were very narrow distributions and approximate the integral, saying that the integral will be dominated by momenta, these integrals, right, will be dominated by momenta close to this value. It will be the same. It's just much easier to use a Dirac delta, right? That way the result is exact for a Dirac delta. But remember, we're talking about narrow states. So no plane waves. KB, PB. So I'm assuming that particle A comes with a narrow distribution, a fairly well set momentum, and particle B also comes with a fairly well set momentum. If I plug these two in here, right, I can do these two integrals. Remember, I have an integral in 3Ka and an integral in 3Kb. These two integrals go away, and I can write now my differential cross section as, I'm just pulling all these factors out now explicitly. So there's a 2AA, 2AB. Remember now these two energies are calculated with PA and PB, not K. Right? There's this difference in velocities, relative velocity of the two particles. There's this that I'm keeping here, right? I will only integrate in this factor once I want the full cross-section, right? So this is what makes this cross-section differential, right? There is this factor, which comes down here, and now I just have to exchange K for P, PA and PB, right? And this one that I'm carrying around because I like energy and momentum conservation, to be very explicit. You can see, oh, also I need to exchange PA plus PB here, right, for momentum. And you see, I will only really use this one when I go to the full cross section, because when I'm integrating on these guys, then I can use that energy and momentum conservation. That's the best way of doing it, because this expression for the cross section is still very general, right? The only assumption I'm making is the one that I have to, because otherwise my particles will never be isolated, and then I don't know how to calculate a scattering between particles that are never isolated from each other. So this actually makes sense. This expression is going in a very good direction, right? Because we have a lot of quantities here that are Lorentz scalars, right? They're invariant under Lorentz transformation. So this guy, by definition, is, you can see when we defined it, is invariant under Lorentz transformation. This one, we know it's invariant under Lorentz transformations with delta 4 here, right? And this one is that Lorentz invariant integral measure, and it will be invariant once I do the integral in momenta, right? So if I take the integral of this, that's a Lorentz invariant. Right? And in fact, that's what we call anybody invariant phase space. We usually write it like this, d pi n, right? Which is defined as these three guys. Let me just because this is a Lorentz invariant and contains all the kinematic information, right? It shows how the momentum, the momenta can be distributed just based on conservations, right? So this is kinematic information. In here I have dynamical information, but there is a piece here. This piece is a little bit bothersome because we like Lorentz invariants, and these velocities here and these energies do not look invariant at all. But if you think of how I got here, I really choose a reference frame in the middle, right? I took a direction in which these two particles were walking, and I took a distance between them in the transverse plane. So I was really looking at a lab center, a lab reference frame. The two of them were moving, and I put an axis along the direction of movement. So I broke Lorentz invariance when I did that, but the way I calculated, right? To see how this would look if I didn't do it, I can rewrite it, right? I can rewrite it. Let me put it down here and rewrite it in the following way. First, these factors of 2 don't matter, right? They are Lorentz invariants, right? I can put this A times AB inside, multiply the velocities, right? When I multiply the velocity, I get a momenta. So this is EB, PA in the z direction, minus, because this velocity was in the z direction, right? EA, PB in the z direction. And then these I can write in this way. Right? Epsilon, the totally anti-symmetric tensor, right? Mu, nu, or actually mu x, y. So x and y are really the numbers, right? The directions y and x. Nu, pa, nu, p, b, mu. Right? This could be just 1, 2, right? But I'm summing over the other indexes, right? I prefer to indicate x and y, but if you prefer, it could be just 1 and 2, right? And you see this is an area, right? It has the dimensions of area in the perpendicular, 1 over area in here, but the total direction is area in the xy plane, right? So this is an area which is transverse to the z direction and transforms under boosts just like an area would. I mean, it's invariant for boosts in the z direction. You can see that here, right? But it's not for boosts in the other directions. That's a consequence of the reference frame I chose before, right? And now I can write the Lorentz this in a Lorentz invariant way, and then specialize for our reference frame and show that you go back to that expression, right? So if you write AA, EB, VA minus VB, and call this is 1 over F, right? Then I can define an object which is F squared, which is just PA, PB squared minus MA squared, MB squared. These are the rest mass, right? Which you can easily show that you can write like EA PB minus EA EB PA square minus P1 cross P2, or actually PA and PB square, right? Which goes back to that expression when PA is parallel to PB, which is what we assume, right? We went to the reference frame where these two momenta were parallel to each other, right? But this is the Lorentz invariant way, now explicitly Lorentz invariant way of writing this quantity, which is called the Molar invariant flux. I don't know if I'm pronouncing Molar in the right way, probably not, but if you know where I can find the pronunciation for that, leave a comment below, right? Which completes my journey into the dark side of the YouTube, now that I'm asking for comments in the video. So, well, the point here is now I can use this back into the cross-section expression and write a cross-section that is useful in any reference frame, right? So let me write the full cross-section, which is a Lorentz invariant, as 1 over 4, the Molar invariant flux PA scalar PB square minus MA square MB square. The n-body invariant phase space, D3PF 2 pi cube 2EF the matrix element. By the way, we usually, this is not the S matrix, right? This is the dynamical part of the T matrix, speaking strictly, right? But we usually call this the S matrix, right? Or the element matrix, matrix element, right? Despite not being the full S matrix, but it is what matters to us, right, for scattering. 2 pi 4, and this is just the conservation. PA plus PB minus PF, right? This is a very general expression for the cross-section of two bodies, two particles going into, I don't know, any number of particles. You have to specialize for the number of final states when you decide what you want to calculate. Right? It's a pretty useful expression because it now can be specialized to any reference frame too, because it's written in a Lorentz invariant way. Many times we use the Miller flux factor in this way because it's usually what the geometry gives us, but other times we use it like this as convenience dictates. One important thing here is to pay attention to these integrals, right? Because I'm integrating over all momenta. That means if you think only of the direction of momenta, I'm integrating over the whole sphere, right? I'm taking all the directions this momenta can go. But that is tricky if I have identical particles in the final states, right? Because if two particles are identical, as I'm summing over those angles, right, I'm bound to take a combination of momenta, say, where particle A is going into that direction and B in this one, and the opposite. And this, if these two particles are identical, is the same, right? This is exactly the same end result, and these are not two different events. So I'm counting it twice, right? There are many ways that I can deal with that. One of those would be to just integrate for one of the particles over half the sphere and take the other half for the other particle. Be careful, take forward direction in the sense of the direction where the beam was going. For one, with two particles that's quite easy to divide, but with three gets trickier, and with four trickier still, right? So the best way of doing it is really, so let's start with the case I have only two particles. If I integrate over everything, I double counted every, I basically got twice the cross section, right? So I just divide by 2, right? I leave the integral over the whole sphere, but I divide by 2. With 3 particles, what I'm doing is I'm not counting it thrice, but actually 3 factorial, right? Because there's 3 factorial permutations I can make with these 3 identical particles. So that's the amount of times I'm counting the same event, right? So I can divide by 1 over 3 factorial, right? So this expression is true as it's written, right? But you need to be careful about the integrals. The easiest way of doing it is really to integrate over all momenta, but if the particles are identical, you have to remember that you integrated over more final possibilities than really there are, and you have to divide by 1 over n factorial, where n is the number of identical particles in the end, right? Since I'm not specifying the integration here, this is not wrong as it is written, even for identical particles, but you have to be careful with the region of integration. So now, just to specialize this expression to a very useful case, which we use a lot, right? And also allows us to look a little bit further into how these cross sections are useful. Let's think about the 2-2-2 scattering, right? So now I'm thinking of a situation where I have 2 particles at the start and 2 particles at the end, right? And let's see how I can simplify the expression. The situation is now this, right? So I have incoming PA, PB, right? Interaction happens here, and then I have an outgoing. This should be back to back, but I cannot draw, right? P1 and P2, right? I went to the center of mass reference frame here, right? So the invariant phase space is the space of 2 bodies, right? It's on the final state, which will be just this part, right? Will be the integral of d3p1, d3p2 over 2 pi to the 6, 4, because I have 2 factors of 2 here, E1, E2. Then I have this part, 2 pi to the 4th, and I will separate the 3 momenta from the energy, right? So the delta for the 3 momenta is just PA plus PB minus the sum of final momenta, so P1 and P2, right? But since I am in the center of mass, PA plus PB is 0, right? Again, the advantage that this is an invariant phase space is that I can choose my reference frame, and this is the best one to do it, right? PA plus PB is 0. Then the part of energy, which is just EA plus EB minus E1 minus E2. This I'll call the center of mass energy, which is a very useful quantity, usually well known in experiments. And when you hear about accelerators, it's usually about this energy they are using to tell you how powerful the accelerator is, right? So this delta will basically make so that P1 is minus P2. So this is trivial, right? It's what you expect from momentum conservation. And that I can use to integrate in 3 momenta 2, right? That integral goes away with this delta, right? And I'm left with the integral in d3p1, which then I'll write in spherical coordinates. So I have dp1. So this now is the module, the module of p1. I have p1 square and the solid angle, which are the other 2 variables of integration here. There's a bunch of factors of 2 pi here. If you do it properly, it's we have a 16 pi square now, right? E1, E2, and this delta, which now is just delta of center of mass energy minus E1 minus E2. And of course, in these energies, I have to remember that P1 is equal minus P2 when I'm calculating the energy, right? Because that was imposed by this other delta. Okay? With these delta in energies, you have to do the same I did a few moments ago to get the Molar invariant flux, right? It's the same thing because I'm integrating P1. I don't want to do the integral in the solid angle for now, right? So that will give me, I won't do it again, the omega p1 square over 16 pi square e1 e2, and there's this factor that comes out of the delta, which is very similar to the Molar flux, which is p1 plus p1 over e2, right? I should have p2 here, but I already using this, right? And this is all, again, remembering that in these energies down here, P1 is equal minus P2, and the E1 plus E2 is ECM. And then I can actually multiply E1 and E2 in here. That simplifies things a bit. There's a P1 factor that I can take out, because there's some cancellation with the P1 square in the numerator here. Notice that I integrated in P1, right? This P1 square is really fixed by these conditions, right? It's a big expression given by what came out of these Dirac delta. Right? So I'm left with the integral over solid angle of this 16 pi square P1 over, once I multiply things here and take P1 out, I end up with E1 plus E2, which is the center of mass energy. And this is a good expression for us. Let me put the cross section here. And actually, this is not the cross section. This is just the n-body invariant phase space. This is the phase space, right? So, but that means that the cross section, the total cross section, has the total integrals, but what is usually interesting for us, then that's why I didn't integrate in these guys. Of course, these guys all depending to angles, right? But is the differential cross section, the sigma, the omega, that I don't have to do this integral, right? In the center of mass is equal to, right? Molar flux, which in this case, since I am in the center of mass, the momenta, the initial momenta are parallel to each other, so I can specialize to that first version of it that we got, which is easier to use in the center of mass, right? P1 over 16 pi square times that information that actually comes from the theory, right? So this whole thing I obtain only essentially assuming kinematics. The dynamics is all here, right? Including the dependence on angle, right? So this could have angle dependency, and I cannot integrate in omega unless I know all of this, right? So that's why I cannot integrate in omega. I was pretending I didn't want to, but actually I cannot go much further before I know if the interaction depends on the angle, if there's angular momentum. I mean, it's complicated. It can be very complicated. I can take this even further without even knowing anything about the interaction if the particles are all identical, right? Suppose that all particles here have the same mass, right? In this case, the energy of the two incoming particles will be the same in the center of mass, right? Which is half, each of them will carry half of the center of mass energy. That means all momenta will have the same module. all of them will have the same module, which I'll call just P, right? And the Molar invariant flux can be written just as EA PB minus PA EB. Then I just use this. This is just ECM P, right? Which means that my differential cross section is just I'll just abbreviate this to this one, just not indicating the particles. And this is 64 because there's a 4 here, pi square center of mass energy square, which is fairly simple formula. But again, you have to be careful, right? I didn't integrate over the solid angle. This is the angle between the two outgoing particles. No, between the incoming particle and one of the outgoing particles, right? Say A and 1, right? And when I go over this angle, I'm also taking particle 2 coming out back to back with particle 1. That means if I go over all the solid angles, I will double count over the final states because these two particles are indistinguishable. So I either do this integral over just half of the sphere, or I do it over the whole sphere, but I have to divide by 2 at the end. So it's important to keep track of exactly how you're counting your final states when you use these expressions. They're fairly simple, but you have to understand. And this is pretty general, right? This is for any 2-to-2 scatterings. I didn't say anything about spin interactions. These should all be inside this matrix element here, which could have angular dependencies, energy dependencies, whatever. So this is a pretty useful. These two are two formulas for cross sections we'll be using all the time, because the 2-to-2 scattering is the most common scattering there is. So be using them all the time. So the last thing I want to do is do the same for the decay width, right? So if you remember, I had defined the decay width as the number of decays, the variational number of particles over the total number of particles in a unit of time, which I'll write like that. Right? I can read this as the total decays for a sample with a lot of particles, or as this ratio could be written as the probability of decay of one particle, right, in that sample. And of course, now if I want the differential decay width, say I want to know the probability of decaying a particular combination of momenta, then this will be written like this, which is the same object I had before in the case of the cross section, but now I have this extra factor of 1 over delta t, right? And the fact that this is just 1 to n body. So I can write the differential decay width as 1 over delta t. And this is a very similar expression to what we had before, but now in the case of just 1 to n particles. So let's see what changes. This is just the differential of the moment of the final states. It's the same as we had before, because I'm still keeping full generality in this case. Right, I'm I'm keeping full generality in this case, and I'm here is the factors for the initial state. So again, I have a D3 Ka. Now I don't have Ka and Kb because it's just one particle in the initial state. 2 pi cube phi a of Ka square root of 2Ea integral D3 Ka bar 2 pi cubed phi star of Ka bar square root of 2Ea bar. Same thing we had before, now just one K, right? And then the matrix elements, right? Out PF Ka in and out PF Ka bar in star, right? This is the complex conjugate. Now again, it's the same game. I have to do all this momentum, all this momenta integral, right? And I have some Dirac deltas now. Now I have 3 integrals here, 6, right? And I have 4 for 8 Dirac deltas here. 4 of them I'll keep, just the conservation of energy momenta. So I want to use these 4 Dirac deltas to integrate these 3 momenta. You see there's one extra Dirac delta here, which we'll see what I do with that in a moment. Notice also there's no impact parameter here, right? There's no sense in keeping a free phase here now that I have only one phi, right? So in terms of deltas, what do I have there, right? I have a D3, for instance. Out of here, I can pick up a D3 PF minus Ka, and out of here, I can pick up a delta 3 sum of the final momentum minus Ka bar, right? Together, those imply that Ka bar vector, right? I'm picking up the 3 momenta here. Vector Ka is equal to Ka, which allows me already to simplify a lot here. This also implies, because I'm taking the 3 components of momenta, right? That also implies that the energy is the same, right? Which now complicates the extra delta, because the energy delta, I have one from here, Aa minus sum of the final ones, and one from here. But now already I have that the bar here can be removed. So these 2 deltas, one implies that the other is just a delta of 0, right? Which is not a problem, it's actually expected. Notice too that from these 2 factors, this one I'll keep in the final answer, right? Sum of PF for momenta. This one I'll keep till the end. This is the one I'm messing with, right? Delta 4 of whatever. Already in the factors of 2 pi, I have 2 pi cube here that I'm concealing with 2 pi to the 4th. There's a factor of 2 pi also being left over here that does not conceal with anything. What happens with this delta 0, right? I can think of that. This is a delta in energy, right? I can think of that as using just the fact that delta E, let's write it like this, right? Because it's really what is happening, right? I can just substitute EF by EA here, right? And write this as a Fourier transform. E minus E t. Of course, when this is 0, this is 0, this is just an integral. That gives me an interval in time. I'll discuss now what that interval is, but it must be the same as this one up front here. So it goes away. But essentially, this delta is becoming a integral over all the time, but not, and that, now you have to qualify. Is this the whole time, or is this just a finite time interval, right? And we'll see it's the finite time interval, which makes sense when you do a perturbative calculation for this. So with that in mind, notice because we didn't have the impact parameter and we got no Miller flux factor, right? There's just no factor to appear here. And we are left with a cross section. Now that I can make this guy equal to this one, these square roots combine. This factor is gone, right? This one that was left over here was absorbed to become delta t. I can write this stays, this comes over here, but now is square, and the square root goes away. And what else? Okay, 2 pi to the 4th delta 4 Ka minus sum over Pf, which is the energy momentum conservation, which is I want to keep there. Now I do the same I did before, right? I assume this state was fairly localized in momentum, that there was a well-defined momentum. That becomes a 2 pi cube delta, which goes away with this 2 pi cube and allows me to exchange Ka for Pa. I'm assuming this is the distribution with a fairly well-defined momenta, right? And then I can do this integral using the shape of this function, and then also I'll specialize because this was defined in the rest frame of the initial particle. So EA here is just the rest mass, right? So that means I can write the differential width as 1 over 2 ma. This is coming from here. This stays here. This integral is gone. 2 pi cube conceals with the normalization of this guy, and I have energy and momentum conservation. But now I have Pa here, and this is the expression I was looking for, which, I forgot an important thing here, right? Besides the deltas, these guys have invariant matrix element, right, which is from Pa to all of Pf, right? And once I made the bars equal to the K bar equal to Ka, this became a modulus square, right? So now, of course, this has to show up here. Otherwise, I have no information from my interaction, right? So this is the dynamical information. I was forgetting it in this expression. So it's there. Let me box this. Now, one thing that we need to, make careful discussion here is about this time, right? This time interval, because when you think of scattering, right, you also assuming two particles start, they are far away, I go to the infinite past, they go from the infinite past, they interact here, and they go to the infinite future. What means an infinite past for an unstable particle that will decay? If I throw it to the infinite past, it doesn't exist, right? So I need to be more careful with this, right? So essentially, what I am assuming here, this particle will have a lifetime, right? Let's call it tau. And let's assume this tau is big compared to some time in which, let's say I look at the moment the decay happened, but I don't know exactly. There's some uncertainty on when the interaction happened, right? That's what I'm calling this interval delta t, right? I know the particle was there before. I know I see some decay products later, but I don't know exactly when it happened. If I put some uncertainty about this time, I can assume the interaction only existed there, because I know for sure the particle didn't decay before, and I know for sure it does not exist afterwards, right? If the lifetime of the particle is big enough, right, then I can do this. I can find an interval and assume, right? This is a trick of the calculation and allows me to do a perturbative expansion and treat this just as a scattering, where I have a free particle first and decay products later, which are also free, right? So essentially what I have to do is that this time, and again, there's a kind of uncertainty principle here. The energy, which is of the uncertainty on the energy involved in this process, which is similar to, 1 over this time, right? Needs to be much bigger than 1 over this lifetime. And what is the energy involved? It's the mass of the particle, right? If I go to the rest frame of this initial particle, the energy is basically proportional to the mass. So there's this comparison, right? And this is again of the scale of the width, the total width, right? So there's interplay between the mass of the particle. Now I'm putting these squiggly lines, which means hand waving relations, right? Hand waving relations. This is very loosely related, but there's this comparison we can make between the width of the particle and the mass, right? Which allows us to say, well, this is a long-lived particle, is a good approximation to talk about decay width. We'll see that when this is not true, when the width is large compared with the mass of the particle, then it does not make sense to actually talk about width, right? So have in mind here that I did that for the Z. I made kind of a separation between the production of the Z and then the decay of the Z, right? For some particles, depending on this relation, this does not make sense, and what you actually calculate is this. And of course, I didn't explain Feynman diagrams yet, but this is completely different from this. This, I'm assuming this particle became a real particle. It got on shell, and afterwards it decayed. In this case, it was never on shell, right? And actually these two calculations are different, and we'll see about that. We can divide that. We can go from this to this doing the narrow width approximation, which means that the particle must be long-lived. So when you use this calculation, you have to keep that in mind. You're assuming that particle lived long enough to be treated as a real particle, right? So it was not interacting for a while. And that's what we have in mind, and that's why it makes sense to define this time interval here and the chance that particle decayed in that time interval, which is what I did here, right? Right here. So we'll go back to this discussion once we define virtual particles and off-shell particles, and we'll discuss that again. Well, I think this is it for today. See you next lecture.